first GEOTOP-A seminar of 2023, where we have the great pleasure of welcoming Chazal from INRIA and Université Paris-Saclay, who will speak on measure vectorization for automatic topologically oriented learning with guarantees. I look forward very much to hearing your talk, Frédéric, and please go ahead and speak.
Okay, thank you for the introduction, Catherine, and hello everybody. And I'm very pleased to be here with you and to give you this talk. So if you have any question during the talk, or if there is something you don't understand, just feel free to interrupt and to ask me question, even if it's not completely easy when we are remote. Okay, so what I'm going to talk about is a small work we did with two colleagues, in fact, now 2 years ago, Clément Levrard, who is at Université Paris-Saclay, Cité, and Martin Royer, who was a member of my group 2 years ago. And the motivation for this work was the following, in fact, is that I'm not going to recall what persistence is, because I guess everybody here knows or has heard about it. But when you want to use persistence, when you are doing data science or machine learning, there is some, in general, you follow a kind of standard pipeline where you start from your data. You do some topological construction, and you infer some topology about these constructions, and you get topological information in form of persistence diagrams, like the one which is here on the right of the slide, on the top right of the slide. And then there is a next step, which is to try to use or exploit this topological information in some more standard, in some standard machine learning or data analysis pipelines. And one of the problem, a classical problem with that, is that persistent diagram come in general as a set of points in the plan or as a set of intervals when you see them as code barcodes, and they are not well suited to be directly used in a classical machine learning algorithm or data analysis algorithm that require as input linear objects, vectors, or mathematical objects that are living in some vector space or functions or things like that. But it's not possible to use persistent diagram directly in a standard machine learning pipeline. So this question has been considered for a few years now, and has given rise to quite a lot of literature, because in general, when you have a persistent diagram, the question is, how can we convert this persistent diagram into a vector, or how can we find a linear representation of a persistent diagram that is well suited for a machine learning task. And so we need to have some techniques to convert persistent diagram into vectors. And the question is that, so I'm just going to switch to the next slide. So people have been worked a lot on this question, and many techniques and ways to convert a persistent diagram into a vector have been proposed among the literature during the 5 or even the 10 last years. Some, like for example the landscapes or the so-called Betti curves, are some kind of systematic ways to transform persistent diagrams, into vectors. What I mean by systematic is that they do not take into account the data you have at hand or the problem you are considering. And there is a whole zoo of such representation. I've listed a few of them here. Of course, the list is non-exhaustive. So if you are author, or if you have your own representation, it might not be in this list, but of course there are many others. And what people have also tried to do more recently was to find some some ways to represent persistence as vector, but in a way that take into account the data that you have and the problem you want to address, the machine learning problem you want to address. And for that purpose, there is a way, there is an interesting way to look at persistent diagram, which is instead of considering persistent diagram as just point cloud in the plane, like on the left, you can also equivalently see them as discrete measures on the plane. So you just, to each persistent diagram, you can represent each persistent diagram as a measure on the plane, just as the sum of the Dirac's mass centered on the point on the diagram. Note that here, when I'm converting a persistent diagram into a measure, or when I'm considering a diagram as a measure, I'm not normalizing the diagram. So here, I really consider the diagram just as the sum of the Dirac. Its mass is not equal to 1 or to some fixed constant. So there is some. There are several reasons why it is to see persistent diagram as measures. One is that it makes statistics with persistent diagram much easier to do, because when you look at objects that are measures, you can sum up measures, you can average measures, etc. So when, by embedding the persistent diagram in the space of measures, you are not in a vector space, but you are in a space which has some linear structures. There are also more theoretical reason why it's interesting, why persistent diagram can be seen as measure. I'm not going to talk about it. And also another interesting remark is that when you look at all the, or not all, but almost all the representation of persistence that have been proposed among the literatures, most of them can be seen as linear representations of persistence diagram. What I mean by linear representation, in fact, if as diagram, when you see diagram as measure on the real plane, if you have a function that goes from the real plane to some Hilbert space or to some vector space in general, you can define a linear representation of this diagram just by looking at the sum of the value of f on the point of the diagram. Or said differently, in fact, you are just integrating the function f against your diagram seen as a measure. And the advantage of doing this and seeing representation of persistence in this way is that first of all, you can deduce some interesting properties about persistence through representations. But in general, as you can imagine, that representations can depend on some parameters. This gives you a nice framework to develop some methods that are data-driven to choose or to select well-adapted representation from a given distribution or data set of diagrams. And there has been quite a bunch of papers proposing some different techniques to do that. But one point is that most of these techniques that try to learn linear representations of diagrams are supervised, which means that you have a learning task at hand, and you try to learn, and you have a training set, and you try to learn your diagram in light of this problem. And in the objective of my talk today is to go in the same direction as how can we learn vector representation of diagrams or linearization of diagrams. But what I want to do today, or what I want to show you today, is that we can do it in a clever way in a non-supervised setting, which means that you just have a distribution of diagrams, so you have your data, you do not necessarily have a task at hand, but you want to vectorize your diagram in such a way that this vectorization will be able to distinguish between clusters in your distribution of diagrams. So I'm going to make this a little bit more formal. And in fact, all what I'm going to present to you in the following is not restricted to diagrams, but in fact work for any discrete measure in the Euclidean spaces. So the idea here, or the framework in which we are going to work now, is that we suppose that we are given a sample xn, where each xi is in fact a measure in Rd. So this is just an IID sample of some distribution, but the distribution is defined over the space of measures on Rd. And when I'm talking here about the space of measures, I mean the space of measure without any constraint on the total mass of the measure. I'm not asking all the measures to be, for example, probability measures or to have all the same total mass. So in the following, M of Rd is just a space of measure on Rd. And I'm given a sample of such measures. And I'd like to find a way to clusterize this sample of measures. So this sample of measure, if you are in 2D, can be, for example, a sample of persistent diagrams. You have some process that generate some persistent diagrams. And then from this sample, you would like to be able to find a way to clusterize your distribution of persistent diagrams. I will show a concrete example in a few minutes. But as I just told you, it's not restricted to persistent diagram. In fact, it can be what I'm going to present work for any measure. For example, your measure could just be a sample of realization of a point process in Rd. But here we can keep in mind persistent diagrams. And the result I will state will be for a specific case of random persistent diagrams. Can you? Oh, okay. So when you have a sample like this one of measures, and you want to discretize it, a first idea or first direct approach to try to clusterize between a set of discrete measures would be, for example, to just endo the space of measure on Rd with a metric, and then use some standard the metric clustering algorithm, like k-means or hierarchical clustering, etc. But when you want to do that, there are two problems. The first one is that as we are working with measures that do not have all the same mass, it's not completely obvious to know which metric to use on this space, because in general, a natural candidate for the metric is Wasserstein matrix. But for example, this Wasserstein metric requires all the measures to have the same mass, at least in its classical form. And another problem with this kind of direct approach is that if you have a lot of many measures, or if you have a lot of persistent diagrams, computing distances between diagrams and between many diagrams that may also have many points can be extremely costly and make the problem intractable in practice. So when you have this kind of problem, there is another way to try to clusterize, which is to transform your measures or your diagram into vectors, to represent your measure as vectors. So for example, if you have a measure on Rd, you can choose a grid on Rd, a fixed grid, and a fixed sized grid, and you can count the number of point of your measure in each cell of the grid, and you represent this as a vector, as on this small picture, and this is a way to transform your measure into a vector. This is a naive way to transform your your measure as vectors. And then once you are in a vector space, you can use standard clustering algorithm. Another way to counting points or the mass of measures in a fixed grid is one way to convert a measure into a vector. Some other ways to do that are, for example, using what I called in previous slide a linear representation. So you choose a function and you choose a set of k functions defining on Rk, and you integrate your function against your measure, and what you get is a vector. So when I write x of f here, this means that I'm just integrating f with respect to the measure x. And for example, this is a way in TDA you obtain persistent images or persistent silhouettes, etc. Many vectorization of persistence in TDA are obtained in this way. And another kind of vectorization is what I will call kernel vectorization. This is a case where, as for your function, you use a kernel-based function where the function are of the form psi of the norm of u minus cj divided by some sigma, where psi is a kernel. Cj are some chosen centers in RD, some fixed point in RD, and sigma is a bandwidth. So you choose. So the way when you convert your diagram or your measure into a vector here is that you just choose a set of k centers of k points in RD. And then you integrate your this function psi of the norm of u minus cj over sigma against your measure, and this gives you the GS coordinate of your vector. Okay, and this is the kind of representation we are going to consider. And now the question is that when you have your distribution of diagrams, how can we choose these centers in a clever way? So, and how to choose also the bandwidth sigma. So just to give you, and the way we want to do that, so now our goal will be to propose a procedure to find some center Cj, and that allow to vectorize, to do a kernel vectorization of our distribution of measure in some kind of clever way, or in a way that will preserve some, that will highlight some structure, some clusters in our distribution of diagrams. So the theoretical setting in which we are working is that the first thing you need to do when you do this kind of thing is to choose a kernel psi, which is just a function from R to R plus, or from R plus to R plus. And for some theoretical reason, in general, to get some theoretical result, you need to choose your kernel to be close to 1 when you are close to 0. And we need to have it to decrease fast enough. So I'm not giving the exact technical condition we need that are required for the kernel. And you also need your kernel to be 1 Lipschitz. So it has to decrease fast enough, but not too fast. And in practice, for example, you can choose for the kernel the exponential minus u. And now the question is, how do we define, from a theoretical perspective, a good set of centers? And the way we do that is that we consider the so as we have a distribution of measures, x, we look at the expectation of this distribution. So we have a probability distribution of the space of measures, which is represented by the random variable x here. And we just define the expected measure of this distribution of measures as the measure which is defined for measurable set A as just the expectation of the mass of x of A over the distribution of x, right? This is what people in a point process call the intensity function of their process. And the way or the set of centers we are going to consider, we are interested in, is that if I choose to have k centers or to vectorize my measures in dimension k, then I will choose a set of centers that I will call an optimal codebook, which is just a set of k points in RD that minimize the Wasserstein distance between the expected measure of x and the measure which is supported on the set of these k points. Or if you read it a little bit differently, I'm just looking the set of k points that minimize the integral over RD of the minimum among of u minus tj, and when I take the minimum over all the for j going from 1 to k, and I take this integral against the expected measure of x. So this can be seen as my optimal codebook or unoptimal codebook, because it is not necessarily unique. An optimal codebook, in fact, is the best approximation of E of x with respect to the Wasserstein distance 2 by a measure whose support has cardinality k, as k points, by a discrete measure with k points. So that's what I call an optimal codebook. And that's what I want to use as my vectorization of measures. And when we try to do that, there are two parameters to be chosen. One is the number of centers we want to use in our optimal codebook, okay? And also, I did not mention, talk about it, but there is also the choice of the sigma when we, the bandwidth, with sigma, which is the bandwidth when we build the vectorization. So the kind of result we will get in theory for the, in general, are under assumption that state that for k large enough, we can find a sigma such that blah, blah, blah. We will see some example of result. And in practice, we will see on the example, in general, what we do is sigma for the choice of sigma. We just look at the minimum distance between two centers, and we take a fraction, like for example, 1/4 of this minimum distance. And it, in general, works pretty well in practice. So let's see how we can prove something about or get some result using this approach. So we are going to come back to the case of persistent data. So we consider the following model. We have L, capital L, compact submanifold of RD that are given. They do not necessarily have all the same dimension. And we also suppose that we have some hidden label variable, Zi, that takes value in 1L, and some weights P pi L that sum up to 1. The way we are going to generate persistent diagrams here is the following. So we consider for each submanifold SL the distance to this manifold as a function on RD, and what we are interested in is in the persistent diagram of this distance function. We will call it DL. And now the way we generate data with this model is that to get a persistent diagram, what you do is that first you pick at random an integer between 1 and L with probability pi L. So the probability that you pick L, a small L value is pi L. And once you have selected your L with probability pi L, then you uniformly sample on SL a set of NL points where, okay? So the model here is that you have a mixture of manifold, you have a set of manifold, you randomly choose one of them system. You sample n point on this manifold at random, uniformly, let's say uniformly, according the you use the volume form, for example, on your manifold, and you sample according to it. And then you get a point cloud, and now you compute the persistent diagram of the distance to this point cloud. And this gives you a random. In fact, you get a kind of mixture of a random persistent diagram, because depending on which manifold you have selected, you get different kind of persistent diagrams. And so that's the idea. And now we suppose that we have a sample of n such persistent diagram, and we would like to see if how the procedure as just described before allow you to clusterize your diagram in such a way that we recover the L different classes that are hidden in my data, because I have L classes, each one represented the diagram associated to one of the manifolds or on the submanifold. And to do that, there is a small technical thing we have to take care of, is that in general, when you consider a smooth submanifold, compact submanifold of RD, and when you look at the distance to this submanifold, when you compute its persistent diagram might be infinite. It might have an infinite number of points. So that might be could lead to a problem in the analysis of the algorithm. So what we do to avoid this problem is that, in fact, of considering as our input measure the persistent diagrams, the objects we consider is that what we call the thresholded persistent diagram at scale S. So we just keep in the diagrams the points that are at distance at least S from the diagonal. So what I denote here by DLS is just the persistent diagram of the distance to SL, where I remove all the points that are at distance less than S from the diagonal. By doing this, I'm sure that I have some finite persistent diagram. So I have some measure with finite mass, total mass. So now the idea, and sorry, so that's one parameter that I choose, S, which is I threshold my diagrams, so or my measures, and so this S is for the underlying model, for the true manifold, and when I have my samples on the manifold SL, I look at the diagram obtained from the sample, and I do not threshold them at S, but I threshold them at S minus H, where H is some constant, which is such that H is larger than 1 over n to the 1 over dl, the number of points that are sampled on the manifold. So this is some kind of extra parameter that I use for to go from the model to the discretization through the samples. And the idea behind all this is that the first remark is that if H is small enough, and if I sample sufficiently many points on a manifold, as you probably know, the stability properties of persistent homology tell me that the persistent diagram I'm going to compute with my point sample on SL will be close within to the persistent diagram sample built associated to the true manifold SL. And the distance between both, or the bottleneck distance, will be H. So for H small enough, and if you sample sufficiently many points, what you get is you get a persistent diagram which is close to the true one, except maybe in the bound parallel to the diagram, in the set of points that are at distance less than H from the diagonal, where you can have some extra points that are not really associated to the true persistent diagram. And a second idea is that, of course, by considering the persistent diagram of our samples and trying to clusterize them, there is no hope to recover the right clusters if two of the manifolds in my model, S1, SL, have exactly the same persistent diagram. Because as we are just looking at our manifolds through persistent diagrams, so to be able to establish some results, we need to make some assumption about our model, and we need to assume that our shapes can be discriminated through their persistent diagram. So what I mean by this is that we can introduce the following notion that states that our family of manifolds, S1 to SL, these manifolds are discriminable at scale S. If whenever I take two of them and I look at their persistent diagrams, I can find one point which is in the persistent diagram of one of the two and not in the other one. In terms of measures, this just means that I can find a point whose measures with respect to the persistent diagram of the first one is not the same as the measure of this point with respect to the persistent diagram of the second one. So if I'm doing this, I'm sure what I'm just saying here is that when I remove all the points that are distant less than S from the diagram of my submanifold, I can still distinguish the manifold through their persistent diagrams. There are not two of them that have the same persistent diagram. So that's a kind of natural assumption I need to make. And I need to introduce also a few more notations to state some results. So one more notation is that for each diagram of, for the diagram of SL, dl of S, when I look its total mass, which is just the number of points of the diagram, in fact, I denote it by ML, and I denote by M bar the average number of points in the persistent diagram of my mixture of submanifold. So just the sum of the pi L ML. And I also denote by pi min the minimum proportion, the minimum of the pi L's. And I recall you that pi L is the probability when I pick one of the manifold that I take the manifold L. And now I assume that my mixture of manifold is discriminable at scale S. And I choose K0 point, M1 to MK0, that are discrimination points. That means that these are the points that allow me to discriminate between the different pairs of manifolds. And now I need to introduce another quantity or another integer which depends on H, which is K0 of H, which is just the smallest number of balls of radius H I need to cover the union of the diagrams of all the submanifold minus the discriminative points. So I have K0 discriminative points. So K0 is upper bounded by L times L minus 1 over 2 because I have this number of pairs of manifolds. And I look now at the points in the union of all the diagrams that are not discriminative points, and I call K0 of H the smallest number of ball I need to cover, of radius H, to cover this remaining points in this union of manifolds. And a first result we can state in this case is that if I choose K larger than the sum of K0 plus K0 of H, an optimal codebook built with K points associated to the expected measure of X will satisfy the following property, is that if H is small enough, I'm sure that one of the centers of this optimal codebook will be close to for each discriminative point, I will be able to find the centers of my codebook close to this discriminative point. Or by close, I mean at a distance of order h of the discriminative points. So this first result just tell me that if I take k a sufficiently large number of centers, when I consider an optimal codebook, some of the centers in this optimal codebook will be close to the points that allow me to discriminate between the different persistent diagram of the underlying manifolds. And when I have this, it's not very easy to prove that if I use this optimal codebook to vectorize my persistent diagrams using my kernel, my exponential kernel, and if I choose a bandwidth which is of order the minimum distance between the discriminative points, then for if h is small enough and if k is large enough, with high probability, I will be able, when I look at the vectorization, to distinguish between the persistent diagram that comes from different manifolds. So written in this way, if I have two vectorized persistent diagrams that come from the same manifold, then the vectorization will be at distance less than 1 quarter. And if they come from two different manifolds, sample manifold, then the distance between the two vectorization of this diagram will be larger than 1/2 with high probability. This means that now if you try to clusterize your vectorization with any simple algorithm, like for example even a simple single linkage algorithm, you will be able to recover without any problem, perfectly recover the cluster associated to each submanifold. So that's first result. But now this does not give us a completely practical procedure to do that, because we don't know, we don't have access to this optimal codebook. We don't know the expected measure E of x, and we don't know how to get the optimal codebook. So, but by chance, we can approximate this optimal codebook. And the way we approximate optimal codebook is by generalizing the standard Can-Mean algorithm to distribute. So the Can-Mean algorithm is working for a distribution of points in RD, and we can, in a straightforward way, extend it to distribution of measures. So just to remind you, when you use the Can-Mean algorithm, the way it works is that for points, when you have a distribution of points like the one here, you just choose your number. You want a clustering with k clusters, so you just initialize the at random, for example, k centers, and then you iterate in the following way. For each center, you look at its Voronoi cell, you look at the mass, the barycenter. So you look at the points that are in the Voronoi cell of a center. You look at the barycenter, so the expectation of your distribution in this Voronoi cell, and then you move your center to the barycenter of its Voronoi cell. And then you iterate this until you get something stable. So this is a standard Can-Mean algorithm. And in fact, you can extend it in a straightforward way to distribution of measures. So again, you initialize, for example, and there are two versions of this algorithm. The first one, which is a standard one, which is called the batch algorithm, is the one where you consider all the data at once. And this is a Lloyd's algorithm. So you initialize at random your centers, and then you compute the Voronoi cell of your centers, and then you look at the expectation of your distribution with respect to the empirical mean measures, where your xi now are your persistent diagrams or your discrete measures. So in practice, this is exactly the same algorithm. And then you stop when your centers are stabilized. So that's the first version of the Kamin's algorithm, which might be a bit costly if you have a lot of many measures or many diagrams with many points. And there is another version of this Kamin's algorithm for which is called the McQueen's algorithm. And this is a mini batch version of this algorithm. So the way you proceed is a bit different. You split your set of persistent diagrams into T subsets. So you make a partition of your set of persistent diagram in T batches, mini batches, all of the same size. And now the way you do is that you start from your centers at random, and then you iterate on the batches, and at each iteration, you move your current centers towards the barycenter of the a little bit towards the barycenter of the Voronoi cells of your batch. So this is a kind of batch version where you don't, the way you iterate is you iterate on, so when you use this mini batch algorithm, you just have to look at your whole data just once, because you split your data and you iterate on the subset of your data. And now the question is that by doing this, do we get some, when we look at the outcome or the output of this algorithm, do we get some things which is close to the optimal codebook of the expectation of X? And the answer is yes, but for this, you need to make some assumption on your measure. And these assumptions are called what are called margin conditions on the expected measure on E of X. So to define it, we need a few, just a couple of definitions. So suppose that we have a random variable taking its value in the space of measures that are supported in some ball of radius lambda and whose total mass is upper bounded by some constant m. So we can look at the expectation of X, which is a measure, and we define B as, so when we are given a K, we can look at the optimal codebooks associated to E of X, and we call B the minimum distance between two centers, between two code words in this codebook. Between two centers, so we call this minimum distance B. We call P min, which is the smallest mass of the Voronoi cells of the centers in the optimal codebook. And we denote by N of C star, which is just the skeleton of the Voronoi diagram. So you look at the intersection of the closure of all the cells of the diagrams, you take their union. This gives you the skeleton of your Voronoi diagram, and we call it N of C star. And with this definition, we can define the notion of margin condition for a measure or for E of X. So we will say that E of X satisfies a margin condition with radius R0 if for any T between 0 and R0, when you look at the total mass of the skeleton of the Voronoi diagram inflated by T, when you look at the T offset of the skeleton of the Voronoi diagram, so you inflate the skeleton of your Voronoi diagram by T, you look at its mass with respect to the E of X, and you ask this mass to be no larger than T times some constant, to be no larger than some constants times T. So this is a kind of, if you're not familiar with this kind of margin condition, this is the intuition or the meaning of this kind of condition is to tell you that most of the mass, in fact, of your distribution is located around the centers. And in some sense, the Voronoi cells of the centers are pretty well separated. You don't have too much mass around the boundary between the Voronoi cells. So now, with this margin condition, if the E of X satisfies the margin condition, then you can prove that using either the batch, if you use the batch algorithm, when you stop it after log n iteration of something of order log n iteration, 2 log n iteration, then with high probability, you will, the risk will be close, you will be close to the optimal risk in a factor of 1 over n. Here you have some explicit constant, but the important term here is that you get something which is in 1 over n, where n is the number of the sample diagram that you have. And with the mini-batch algorithm, you get a similar result where the bound, so the difference between the optimal risk and the risk coming from your algorithm in expectation is upper bounded by something in log n over n. And so that tells you that if you take sufficiently, a number of samples is sufficiently large, the optimal code book you will get using this K-means algorithm for measure will be almost optimal. There are some assumptions I don't have time to discuss a lot, but this works if your initial guess, for the centers is not so too far away from the optimal codebook. If you are too far away, it may happen that you don't get convergence. But here the idea is that if you start not too far away from your optimal codebook, then your algorithm will converge towards the optimal one. And I don't have time to discuss this, but in fact, these bounds are optimal in the sense that with this kind of model and kind of margin condition, you cannot find an algorithm that will lead you to convergence rate which is better than 1 over n. Okay, so that's it for the theoretical part. So I'm just going to conclude with just show you a few experiments. I just want to mention that these results are mainly theoretical results because in general in practice it's very difficult to check, or in general we don't know how if the assumptions that we have made like the margin condition and these kind of things are satisfied. But as often with K-means algorithm or this kind of algorithm, they work pretty well in practice. And the main advantage is that they lead to some very simple algorithm, very efficient and fast algorithm, and very easy to implement. And I'm just going to show you 2 experiments that illustrate it. So these experiments, we implemented them in an algorithm on a protocol which is called Atoll, and which is available if you want to try it with your own data. For example, it is implemented in the Goody library. So the idea is that you have n measures, discrete measures. The user has to choose k, and then you build your codebook using the mini-batch algorithm I just presented before, and you vectorize your measures using the vectorizations we have studied, just by choosing for sigma 1/2 of the smallest distance between the points of your codebook. And then you get vectors, and you can use your favorite clustering or learning algorithm to process this vectorization of diagrams. And here we did it. The first example here is not for persistent diagram. It's an example with discrete measures that are not diagrams. And what we did is that as a data set, we use what is called the large movie review data set. So this is a data set where that contains 50,000 reviews of movies. So these are text. and each movie is labeled. So these texts are reviews about some movies, and each text is labeled with a positive or negative tag. Positive is a review is positive, and negative is a review is a negative one about the movie. And now, when you have such a review, which is a text, this is a collection of words. So you can see it as a bag of words. And now, what we did, we use some standard techniques to convert word into vectors. The one we use is a popular one, which is named word2vec. So this is a technique that takes a word and embed it into a space of, here we choose a dimension 100. So in R100, we embed the words. And now, when you have your text, you get a bag of words. And each word of the bag is embedded into R100. So for each data item, which is a text, you get now a set of points that you can see as a measure in R to 100. And then we used Atoll with case centers here, and so we got some vectors of dimension 20 represented each review, and then we use a very simple neural network with just one layer to classify the reviews. And what we obtained a classification score of something like 85% of good classifications, with a standard deviation of about 1%, plus or minus 1%. The point is that when we look at this result, of course, these are not state-of-the-art results. For example, there are some techniques we compare to a technique that use an architecture which is called LSTM, which is more dedicated to process the text data. And with this kind of architecture, we get some slightly better score, which is around almost 90% of good classification. And if you look at the state of the art on this kind of data set, it's almost 100%. But this is not surprising, because with Atoll here, the way we did it did not take into account that when you look at the text, there is a kind of, the words are put in some specific order. And this, the procedure we used, forget about this, while the recurrent neural network like LSTM take into account this information. So this is not surprising that we don't get state-of-the-art result. But the interesting point here is that by just doing this very simple procedure with Atoll, we already get some kind of pretty good result on this kind of experiments. And even more interesting is that when we look at the times, the running time of this algorithm, with Atoll, it takes something like 5 seconds to get the centers, to get the quantization. It takes like 200 seconds to compute the vectorization of the vectorization of the measures, and then in something like 350 seconds, you train your network and you get your output. While if you use an LSTM on the same data set, to get the score which is here, you need the average time to run this, to train this kind of network is about 1 hour. So which is significantly longer. And if you look at the state of the art on this data set, the training time takes something like almost 10,000 seconds. So Atoll here is, the procedure is so simple that it is very fast. And I think I am not far from running out of time. I will just show you a last example where we use persistence. So it's for large scale graph classification. So here the problem is that we have graphs which are just represented as vertices and edges. And the way we transform a graph into measures, or a way we associate a persistent diagram to a graph, is that we use something which is called hit kernel signatures on the graph. This is is some function which is defined on the vertices of the graph, which is associated to diffusion process on the graph. And you can, if you don't know it, you can just think that we choose some functions, some on the graphs. And here we choose, so for the head kernel signature, we choose 4 different times. So this gave rise to 4 functions on our graph, on the vertices of our graph. And the way we convert this information into measures, there are 2 ways to do that. One is just to say that when you have I think there is a mistake here, but when you have a graph, you compute these functions. You have a vertex. For each vertex, you have, let's say, 4 values, which are the value of this function. And then you can embed each vertex of a graph in R4 as a point. And if you do that for all the vertices of your graph, and then you get a point cloud in R4 that you can be considered as a measure. So that's one way to do that without persistence. And another way to do that is to, as you have function on the graph, you can compute the persistent diagrams of these functions, and then you get persistent diagrams that you can see as measures on the plan. And this is 2 ways to represent your graphs as discrete measures. This is what we did. And then you can train Atoll on this vectorized information. So we did, in fact, the way we did it is not by choosing 4, but 2 times, diffusion times. We choose 10 centers, and as we had 4 functions, we get an embedding of our graph into R to the 80. And then the way we run classifications after that is just by using standard random forest. And when we apply this method on different graph data sets, and here on in this table, you have the result of some classical method for graph classification, and you have the result for Atoll. And as you can see, in some cases, Atoll overperform is much better than these dedicated method. Like for example, for the GitHub Stargazers database that contains more than 12,000 graphs. For the classification score are better by more than I think 6 or 9% than the one provided by some other state-of-the-art methods. And in some cases, this is not the best, but it is never very far from the best scores. And this without using anything very sophisticated. So it's a very simple naive. And the same result on some other graph databases where there are not only 2 classes, but with several classes. And we applied Atoll either with the persistent diagram seen as measure or either directly on the functions also seen as measure. And you can see on some different graph databases, both methods obtain state-of-the-art result compared to some other existing methods. Okay, so it's time to conclude. So just to recap, what I've presented to you is a very simple method to vectorize persistent diagrams in a data-driven way, but not in a supervised way. It's a bit coarse, but it's very fast. And it works pretty well in practice when we use it. And that's on the practical advantage. And on the theoretical side, this is a method that comes with theoretical guarantee, even if the theoretical guarantee are still a bit far away from I would say, the real condition we meet in practice. And then I will stop here, and I thank you for your attention. And I just put here the 2 papers that are related to what I presented to you. In particular, for the second one, you have the statement of the result in a much more precise way, with all the constant explicited and all the condition explicited. Thank you for your attention. I'm done.
Thank you very much, Fred, for a very nice and interesting talk. Very really interesting results about how we can get around this problem of vectorization. Are there any questions from the audience? If not, then maybe, Fred, what are sort of the next steps along this path? What are the next things you would like to do to continue to explore these sorts of possibilities?
In fact, there are two directions. One we did not really start to work on, which is on the mathematical side, to see how we can improve a bit the result we got. And I would say this is not a very topologically oriented direction, because this is really to go into more statistical aspect related to quantization of measures and things like that. And another direction we are currently exploring, in particular with Martin Royer, is the application side and methodological side. So now the question is that as this is a very simple and quite efficient way to vectorize persistence diagram or even discrete measures, we try to see if in some specific applied setting it's possible to prove some interesting mathematical result, and also to get some interesting practical result. For example, there are some practical situations where you get some distribution of diagrams, but the way you get this distribution is in a time-dependent way. So you may have time series of persistent diagrams or time series of discrete measures. There are some applications where you get this. And something we are trying to understand now is how can we take into account some kind of time dependency in this kind of procedure to be able to do something even better if you know that your distribution are coming from time series of discrete measures. For example, one example, there are many, not many, but there are many applications in which you have time-dependent graphs. So you consider some graphs, and these graphs evolve over the time. And we know from this graph how to build some persistent diagram or something like that. And this gives rise to a time series of persistent diagrams. And we can apply ATOL to this distribution of diagrams. And now the question is that how can we take into account the time dependence in this kind of procedure to make it useful or relevant, or to achieve the practical goal we want.
That sounds very interesting and indeed highly relevant, because the sort of graphs one looks at in real data do tend to, at least the ones that I see in neuroscience, do tend to vary with time.
In fact, one case I started to think about this, but I didn't. But now we are working on some other case. But one example is that I'm not an expert in neurosciences, but when people are doing EEG, they put several electrodes on the head of people, and they get time series. Each sensor on each electrode give you a time series, and as far as I know, people are building graphs where the vertices are the electrodes, and they put some edges between vertices that are weighted by some correlations between the time series, between the signals, right? And if you look at this and you use a sliding window, you get so when you look for on a window the signals, you get a correlation, and then you get a weighted graph whose vertices are your electrodes, and then the weights on the edges are the correlation between the signals. So now if you start to slide your window along the signal, you build a sequence of graph, a time series of graphs, And the question is that can we and for if you compute some you build some filtration or you compute some persistence on top of these weighted graphs. One question is that are we able to detect some changes in the global structure of the graphs using persistence? And here Atoll is a good candidate to vectorize this time series of graphs in order to do some anomaly detection or to change point detection on things like that.
Sounds great. That sounds like
some colleagues try to do a few experiments with neuroscientists in this direction. For the moment, it's not fully convincing for different reasons. I think that this kind of signal is extremely dirty, so it's very difficult. And also the people do not exactly what they want to get. But with Martin Royer, we are looking at this kind of similar problem in a more industrial setting, where, for example, if you have you are monitoring a system, a physical system with several sensors, you are exactly in the same situation. You have several signals from your sensors. So if you consider a time window, you can compute the correlation between these signals. You can, and then you get a weighted graph representing the correlation between the different signals. And if you slide the window, you get a time-dependent graph. And you might be interested to, and if you want to detect some anomaly in the functioning of your system or some change of regime, it seems that in some cases it can be done efficiently by using persistence or this kind of vectorization of the information you have in the graph. We are working on it. It's still preliminary, but it's quite promising and interesting. And the idea would be to be able to do some maths that justifies the fact that the practical results are encouraging.
Cool. Sounds great. Are there any further questions?
Fred, I have a rather basic question, a curiosity. Of course, to introduce Dirac delta functions to weight points on diagrams is a natural idea. Who introduced this idea? Can you give us a name of reference of some?
I don't know. I can't tell you who introduced this idea because it's considering a finite set of points as a discrete measure. I think probably has been considered by many people for a very long time, and I don't think it's really new. In the setting of persistence, I think that I would say that it's part of the folklore for a while, and in particular, some places. The fact that you can represent most of the linear representation of persistence can be seen as just integral of function against persistent diagram seen as measures. I do not claim that this was the first time, but we used it in a systematic way in a paper with Vincent Divol some years ago, where we wanted to study the expectation of persistent diagrams. There are also some reason to do that, some statistical reason, because when you are considering persistent diagram in the space of diagram with the bottleneck of Arthur-Stein distance, doing statistics is not easy in the sense that, for example, expectations are not well defined, or average or means of persistent diagram are either not well defined or very difficult to compute. And if you see them as measures, you can do the space of measure is a convex set. So you can average measures and get expectation, etc. And another bit further motivation also to consider persistent diagram as measure, or to see them as measures, is coming from the algebraic theory of persistence. So when you want to define persistence just from a persistence module, which is just a sequence of vector spaces connected by linear map. The way you define it is in fact as a measure. It appears naturally as a measure, as the counting measure, defined over the rectangles. But by nature, I would say persistent diagram looks much more like measures than point sets.
Thank you.
Okay, take care,
Okay.
everybody. Have a good weekend.